Hi. In this video, we will look at building a multivariate time series model using vector autoregression. Vector autoregression, or VAR as it is called, is a statistical model used to capture the relationship between multiple features as they change over time. Now, we will go into the details of VAR model. We will look at how we can operationalize a particular insight from VAR model, or basically run the entire VAR model by itself. Also, we will kind of learn more what are the challenges with VAR model. So let's get started. Now, I'm going to import a set of packages. I'm using pandas to import the data set and then just process the data set. Matplotlib for visualizing the data set. And then NumPy is basically we are going to use so that we can take a particular portion of a VAR model and run it manually rather than using the VAR's forecast method. So if you want to take it and just operationalize a particular insight rather than all the features, then we'll just use NumPy. I will show you how you can do it and build a vectorized implementation of it. I am having a couple of packages from stats model. One is the VAR model itself, which we are going to use from stats model library. Then I have Granger causality test. This is basically to check if a time series X causes a time series Y. And I will tell you like how we can apply it before feeding it to the VAR model. I am going to be also importing Augmented Dickey Fuller Test, which is to check whether time series is stationary or not. So these are the packages I am importing. Let me run it and let me kind of download the data set and put it into a pandas data frame. So what I'm doing is I'm reading this data frame. This is a CSV file. This file is available in my GitHub repo in this location, or is this also available in the UCI machine learning repository. The data set is appliance energy usage data set. You can search it. You will find it easily in UCI, or you can just use it from my Git repo directly. Now, I am also passing a parameter called parse dates are true. So this has a date column. The date column is to tell when the particular time series observation was recorded. Now, if you don't give parse date equal to true, it will consider that particular date column by default as object. Just to change the data type to date time, because it's easy for us to manipulate the date time column, slice and dice dates. I'm just converting into date. That's what I'm doing. So let me run the data frame output and let's see what are the different columns available. So if you see, basically this is the appliance energy usage data set, and there are two columns: appliances energy usage. Basically in your home, if you have some appliances, how much energy is consumed by the appliance, and lights is basically how much energy is consumed by the lights. So these are the two columns that we will be forecasting. I will be just forecasting appliances, but if you want to forecast lights also, you can do it. And then if you see over here, we have the column what is the output temperature. Basically the appliances usage depends on the temperature, right? If the temperature is basically lower during winter, then we may be running heater in the house. If it's higher during the summer, then we will be running air conditioner in the house. So some of the factors of appliances and lights energy usage are dependent on the output temperature, the pressure, the humidity, the wind speed, dew point, and visibility. There are a lot of columns, and what we'll see, like which column we can take and use. And for that, I'm going to run multiple tests. But before that, what I'm going to do is, if you see this particular data, it is recorded every 10 minutes. Right, I have close to around 19,735 rows and 8 columns. What I'm going to do is I'm going to aggregate this data to an hourly level so that it's easy for us to see the output, and also like handle data that is easily manageable and visualize as well. Right, but you can run for 10 minutes also if you want, but I'm going to just aggregate at every hour and I'm going to run it. So for that, what I'm doing is I'm using like pandas resample method, and what I'm telling, resample this data to every 1 hour. Now you can say 1 day or whatever time frame you want, 2 hours, 3 hours, 4 hours. I'm just taking like every 10 minutes observation. So like there's 6 observations every hour. I'm just aggregating it to every hour level, and I'm telling take the mean of all the values. So I can tell whether I want to take a median or mean or everything. Here I'm telling take a mean of every value. So it will take basically for this 6 observations at 5 o'clock up till like 6 o'clock, and then take the mean of each and every column. That's what the resample does. So let me run this part so that we now have data at every hour level. Let me like had it, and let's quickly see the data frame before we get next. And now you can see like we don't have the 10 minutes interval, we have data every hour, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock. Right. Now I'm going to quickly visualize the data and see how the data looks like. Rather than going and printing like each and every column and visualizing and doing a plot, what I'm going to do is I'm going to quickly write a for loop and do that. Right. And for going into that, what I'm going to do is by default, the graphs are going to come at blue color. That is a default color. So I'm going to give different color for each plot. So I'm just putting a color list over here, which will have different color I want to show for the plot. And I am creating an create basically an function that will help me visualize the data. In that function, what I'm doing is I am taking all the column data types and column values which are only number. Right. Basically, I'm taking only which are numeric over there, and then I am here iterating over all this particular features that I have got, and then basically I'm just doing plot. So rather than plotting each and everything, there's just a handy function that's going to take all the data frame and then plot at one shot for all the numeric column. Now some of the other things are nothing but setting like how I want the output to be displayed. Right, basically I'm creating subplots, and this is what the subplot is. In the subplot, I'm telling how I want my graph to be arranged, and the color is basically I'm giving what color I want, and this color will be picked from the list that we created. So and then I'm calling the visualize function with our data frame. So let me run the output. You can quickly see like all the graphs printed at one shot once this function runs. So you can see basically all the particular graph is over here. And what I can quickly do is I can see, okay, this is my appliance column. And in the appliance column, we are just given different color. If I don't give that color option, everything is going to be this blue color. That's what you are going to see. Now, if you see the appliance option, we have data from around January till May. Right, you can see in the initial month, maybe the appliances usage are slightly higher than other months. So maybe the initial month, if you see Jan, Feb and all, it's little cold. Maybe during the cold season, you may have the appliance season high. And similarly, you can see the lights as well here. During the colder season, the lights usage are pretty higher, but as it goes down, it becomes lower. And the reason can be during winter, the visibility is less and the lights may be higher. Right, and you can see the temperature also follows the pattern. The temperature are lower during the initial month and then higher. So during summer, it peaks up. During winter, it's in negative degree. And similarly, the pressure also follow the same pattern. There are multiple other variables. Now, I'm not going to go into the details of each and every variable, but what I'm going to do is I'm going to see like which variables we can use for our model, and I'm going to run multiple tests. The very first test I'm going to run is I'm going to run Augmented Dickey Fuller Test, which is to check if a time series is stationary or not. Whenever you're working with an VAR model or even an ARIMA model or even an ARMA model, ARMA model, we need to make sure a time series is stationary. Now, ARIMA model by default has a parameter called I, that is ARIMA. I is integrated, or the difference parameter that is referenced by D, where you can feed in how you want to handle your time series if it is non-stationary, right? So it's built into the ARIMA model, but if you're using other models like ARMA or something like that, you need to handle the stationary of data. The very first thing I'm going to check whether the data is non-stationary. If it's non-stationary, then I need to make it stationary. I can make it stationary by differencing the data, applying a logarithmic function, and the order of difference depending on how our data is. There are a lot of methods to do that. I have a separate video for that in my time series playlist. Maybe I will add it in my comments, which you can watch. Now here what I'm doing is the Augmented Dickey Fuller Test. The null hypothesis is basically the series possesses a unit root and hence it's not stationary. That is the null hypothesis. And the alternate hypothesis is basically the series is stationary. Right. So what I'm doing, since my null hypothesis is series is not stationary, if my p-value is greater than 0.05, then by default my series is non-stationary. I can just take the data and run it as it is. But in case if the null hypothesis is not true, then if in case my p-value is less than 0.05, then what we do is we reject the null hypothesis and then accept the alternate hypothesis that the series is stationary. So what I'm doing is I again created a for loop. Rather than running ADF test for each and every function, I have created a for loop here. In the for loop, I'm taking all the columns that are there. I'm just iterating through all the columns, right? And then what I'm doing is I'm calling the add augmented Dickey Fuller test for with that particular column over here. So the basically this has length of column. It will say like, okay, it will give the value from 0 to whatever number of columns we have, and then it's going to take the first column from the list, and then it's going to run the test. And from the test, what I'm doing, result of 1 will give me p value. So I'm taking the result of 1 and checking if it's greater than 0.05. Then I'm just printing like CS is not stationary and the column name. If it is less than 0.05, then I'm telling CS is stationary. So let me quickly run this one, and then let's see the output. Now if you see, basically all of this data, the series is stationary, so we need not worry about it. It's a stationary series and we can directly use it. Now one thing you need to remember is you need to run multiple tests, and also you need to use your visual techniques to understand whether the data is stationary or not. Sometimes the statistical test might not show it, right? There are other tests like KPSS test and everything which you can use to validate whether the series is stationary or not. But in this case, I can see my series is not stationary, and I'm going to assume that the test is valid as well, right? And as I said, all this are covered individually in my separate videos, which you can find in the comments. Right. Now, the next thing I'm going to see, like which time series causes the basically in our the thing that we are looking at is appliance usage, right? So I'm just going to check like which one of this like basically causes appliance, which are the other time series that causes appliance, and for that I'm using Granger causality test. Now you can try it with every variable, what causes light, what causes temperature. But we know like appliance spike might not cause a change in temperature, right? But a temperature change might cause an appliance usage. So for me, my target variable is appliance. But what VAR allows you to do is it allows you to predict all the other variables also that we feed in, right? So let's go when we go there, I will talk over that. Now what I'm going to do is I'm just setting my y variable as appliances, and I'm going to check what are the other time series in our list that causes appliances value to change, right? That's what I'm going to check, whether there is some relation between my input variable and the output y variable. That's what I'm checking, and I'm checking for max lags equal to 8. So how much lag past I want to go. I want to go t minus 1, t minus 2, t minus 3 till what level? I'm telling go till a t minus 8 and check it, right? So these two variables I'm setting. And in the Granger's causality test, the null hypothesis is basically the x does not Granger causes y. In this case, if the null hypothesis is true, then what happens, like, okay, the temperature does not Granger causes appliance, the humidity does not Granger cause appliances. In case if the null hypothesis is not true, we reject the null hypothesis and accept the alternate hypothesis that basically the x value causes y, right? So again, I'm writing a loop over here, and then what I'm doing is I'm calling the Granger causality test, and then I am basically passing the y value and the column, right? I'm starting from the column I plus 1, and here doing minus 1. The reason is first column is the appliance value. I don't want to compare appliance with appliance. I want to compare appliance with the other column. That's why I'm incrementing and starting from 1, and I'm taking minus 1 because my y value is already taken care of, right? And then I'm giving the max lags. I'm telling run up to 8 lags, and then I am extracting the p value from it, and then I'm just printing the p value for each column. That's what I'm doing over here. So once I run this will give me p value for each column. Now if you see, like, basically our null hypothesis is it does not Granger cause x does not Granger cause y. So if my p value is less than 0.5, that means our we can reject our null hypothesis and accept our alternate hypothesis. Now what I'm checking over here is for my multivariate time series, I don't want to throw in all the features, because the more feature we throw, the more back testing we need to do for each and every feature. So for that, I'm checking which are the relevant feature that possibly causes y, and I'm going to just include that feature. And this is how the output we get. We get a lot of p values here. The reason is we have 8 lags, and for each lag we will get a p value. Now, if you see basically lights, the very first is basically greater than zero point 0.5. So we can we basically the null hypothesis is true. We just like accept the null hypothesis, right? That's what we basically do. Now, rather except, we fail to reject the null hypothesis. We don't accept a null hypothesis. We fail to reject a null hypothesis. Now, the temperature, yes, the temperature causes appliance to spike. And if you see for all the 8 lags, the p-value is less than 0.5, right? So temperature is one variable I'm going to use. Then the pressure, if you see like basically, yeah, the pressure also, like most of the values are less than zero point 0.5, but at lag 2 it's not zero point 0.5. So at lag 2 basically the pressure did not Granger causes y. Now we can include pressure as well if we are taking only lag 1, but what I'm going to do is I'm going to just pick few variables out of it. I'm going to pick the temperature, and then I am also going to pick the wind speed, which basically is less than zero point 0.5 for all the series. Now, dew point, it's greater than zero point 0.5. So in this case, we fail to reject the null hypothesis. Visibility also same. So I'm just taking the temperature and the wind speed over here and appliance. These are the three variables I'm going to take, and I'm going to create my input data frame. Now my input data frame has only these three values. Right. So now what we can do is, now that we have these three values, let us start building our model. So very first thing I'm going to do is I'm going to split the data. Since it's time series data, I don't want to do a random split. I need to make sure my time series order is maintained. So I'm just taking like 90% of the column as my there's a colon here. So from starting till whatever is the length, 90% of the length as my training. And if you see over here, I'm taking the 90% till remaining as my test set. So I have the train set and the test set. I can quickly print the shape. There are 2961 rows over here, and then there are 329 rows. There are three columns. That is what it is, right? Now we are going into the vector autoregression model. Now basically in this case, the VAR model, they are used, as I said, are used in multivariate time series. The structure, the way it is defined is, each variable is a linear function of past lags of itself and past lag of other variables. So what I mean by that, in this case, my y variable 1 appliance in this case, right? It depends on the other variable of itself. Y1 of itself is appliances t of 1. This is the first lag. And then the second variable, it can be temperature, the first lag of temperature. So this equation is only for first lag. If it has a second lag, then you will have like y1 t minus 2, y2 t minus 2. In this case, we have three variables. So you will also have like y3 t minus 1, y3 t minus 2. So depending on the number of lags that your model that your model determines, you may have a equation that big. If you see here, it's nothing but a typical linear regression equation. Y is equal to mx plus c, where we have a bunch of coefficients that we are trying to learn. And that's going to happen for each value. This y1 is for, say, like for appliance, y2 is for temperature. You will have one more equation, y3 in our case, for we have used wind speed, right? So you'll have three equation. So that's why if you see like VAR model is able to forecast multiple outputs simultaneously. Okay, now this is how the equation looks like. Now we have to find out what is the lag that is applicable for our model based on our data. Right, now how do we find out what is the lag applicable? The crude way is to basically run it for all the lags and see where you get the lowest metric, right? We'll be using AIC or BIC metric, which gives the lowest metrics. So for that, what I can do is, there are two ways to do it. The first way is the crude way. I am going to define a VAR model, and I'm passing my train data set, and I'm telling the frequency is a hourly frequency. Okay, and then next what I'm going to do is, basically I am in this case I'm going to iterate through and number of values. I'm just giving 48 or 49. I'm just throwing some number. I don't know what is my lag. It can be 20, 30, 40 or whatever it is. The more the lag, the more problem you have, right? So basically that's where maybe you need to take this problem and define it as a more like an prediction problem, where you predict the future, or a regression problem rather than a forecasting problem. I'll come to that now. And then what I'm doing is, I am calling this model.fit for each and every lag. I'm starting with the first lag, second lag, third lag, and then I am printing the AIC and BIC. Now I can see which lag gives me the lowest AIC and BIC, or AIC or BIC, and pick that one. So once I run this, it's going to just keep on printing me a bunch of output. If you see over here, it is printing me a lot of output. And here it's very difficult to see like which one to pick. All right. So the other better way to do it is, rather than going through and seeing like which one to pick, other better way to do it, there is an method called a model.select order. I have already defined the model var model with an training data frame and the hourly frequency. I'm calling that model and just calling a select order number of lag and printing a summary out of it. So once I run this, it's going to be giving me a table like this in this case. And this table, if you basically see, it's going to print all the AIC and BIC metric and FPA metric, all the metrics, right? Now what I can do, if you see on the top, it says the var selection order, star highlights the minimum. So I can directly go and get where the star is highlighted. In this case, the BIC is lowest at lag 7. So I can use lag 7 for my model. If you come down further, we can see like what are the other metrics. If you see, basically in this case, like AIC is lowest as 26, so I can use 26 lag. Now we may have to try multiple combination, but what I'm going to do is I'm going to go with the lowest lag, which is the BIC metric, which is the lag 7 in my case, right? I don't want to run it for 26 lags. Now I'm going back again, creating my var model with the same parameters, and then I'm telling my model.fit for 7 lags, because I know 7th lag is where I got the minimum BIC metric, right? And I'm getting the results. So once I run this and I print it, I get like a model summary with all the coefficients and everything for each and every output. So if you see, this is how my output looks like. It shows the BIC metrics, it shows the AIC metrics, and it shows for appliances, this is the equation that I have. These are the coefficients, these are the probability, that is the p-value that I have, right? And this is the standard error for each of the variable, lag variable that I have. Now if you see the output, we have 7 lags. So basically you can see from L1 to L7 for each variable, we have 3 variable. So you have lag 1 of appliance, lag 1 of temperature, lag 1 of wind speed, lag 2 of those variables, lag 3 till lag 7, because our order was 7. For each of this, I have an coefficients over here, right? Now similarly, I will have for other variable also. If you remember what I said, for each of the variable, it's going to create a separate equation, right? So now for temperature out, these are my coefficients. Now similarly, I will also have for wind speed. If I basically come down, I will also have for wind speed over here, right? Now this is what you have the residuals also, correlation matrix of residuals that is given down. But now you have output coefficients. The model has trained, the model has found output coefficients for all. Now I can just run the forecasting and predict all the future variable together. But typically temperature and wind speed and all I can get from external sources like weather.com or other websites that gives it for free. I can use that. Reason is, the more output variable we are trying to predict, the more back testing for each and every variable we need to do. Maybe the model has done well for appliance, maybe it has not done well for temperature, or it has done well for temperature, maybe it has not done well for appliance. So we need to go and validate each and every variable in the past. If we are able to get that variable, future value of that variable, then we can go and directly get it, right? So this is how the output looks like. Now what I'm going to do is I'm going to forecast it. To do the forecast, what I need to do is I need to basically know in my training data set what is the past lag I need to go to, so that I can get the first value of my test data set. So what I'm doing over here is I'm getting the lag. The lag is nothing but 7. From the result object that you got, you can just use this k underscore AR, which will give you the lag variable. Now the result is the trained model. I am calling the forecast method. I am going to my training data frame, selecting the last 7 values because I need data till lag 7 to predict the next value. So if I take the last lag 7 value and predict, I'll get the first value of my test data frame, right? And we are going to validate how it performs with the test data frame. And I'm telling my steps as 5. That means predict forecast for 5 further time in the period. In our case, it is going to forecast for 5 hours, right? Now this is how my result looks like. So the result object gives me this 5 values in the future. Now I'm going to compare it against my test data set. So I'm just picking the first 5 records of my test data set. If you see, I'm just going to the train data frame. I'm getting the last 7 values, predicting the first future value. The future value is nothing but the first value of my test set. And this is how the output looks like. If you see over here, the appliance is 60, it has come to 44. But the temperature is 8.89, it has come to 8.92. This 3.16, it has come to 3.99. Maybe it's doing somewhat better in the T out and min speed. But here, the last two values, it's close, but other values, it is a little far away. The reason is maybe the data that we have is not able to completely predict appliance usage. The appliance usage can also be pretty sporadic based on the usage of the appliances in the house or number of appliances, right? But okay, we have a model that is pretty close, right? So this is the model now that we have. Now what we are going to do, say like if I just want appliance, I don't want to predict all. Say I can get the temperature and wind speed from the external sources in the future. If you want to predict all three in the future, then you can use it as it is. Now if I want to deploy only the appliance part, assuming I will get the others, and if you want to deploy it as a typical, you don't want to take the model, you just want to take the coefficients and constant and then build your own equation so that you can vectorize it and run it more efficiently, then that's what I'm going to show you how to do that. So what I'm doing is I'm creating a data frame. I am getting all the parameters of the appliances. The parameters are nothing but the coefficients and constant. The result object dot params will give you all the coefficient object for the appliance. Now, when you saw the result dot summary, you add one for appliance, you add one for temperature output, you have other one for wind speed. I'm just taking the appliance, and then I'm getting the p value for the appliance, and I'm just transporting it and providing it into a df underscore coefficient pandas data frame. So once I print it, you can basically see you have all the coefficients and p value of the appliances, right? You can see from L1 to L7 because we have like 7 lakhs, right? Now there are two ways you can use this output. The first way is take all of this and then deploy all the coefficients and run it. Or you can use the insight from this model to build another model. I will tell you what it is. Now, not all p values might be significant in this case. So basically, maybe some of the lags are not contributing to anything. So rather, you don't want that lag. So what you can do is you can only take the lags that are contributing, and you can just create those lags as features in your variable and then fit a typical linear regression model. That is one way. The second way is you can just run it as it is. So how do we find that which features are contributing, right? So what I'm going to do is I'm going to change the column name to coefficients and p value. That's what I'm doing in the data frame. And then I am querying, in this case, where all the p value is less than 0.05. And wherever it is less than 0.05, I am giving 1 and 0, because if the p value is less than 0.05, that particular it's a typical regression model, that particular feature is basically significant. Right now you can set any threshold for this. You can set 0.10 or any threshold depending on your business need. Not necessarily it has to be 0.05. Right now, if I run this, it's going to basically print me all the ones and zeros wherever the particular coefficient is significant. Now, what I'm going to do is I'm going to take the same var clause, and I'm just going to create a new column in the data frame called valid, and then I'm going to run it, and then I'm going to print the output. Now this output, if you see, it's going to add one more column dot valid, and it's going to, wherever the p value for that particular thing is less than 0.05, it's going to basically put 1. So basically the constant, yes, it is significant. The L1 value, the lag value of appliance is significant. The L2 value of appliance is significant. right? And then the L4 value of appliance significant, and the L7 temperature output is significant. Now think about it, right? The L7 temperature is nothing but the temperature 7 years back, right? 7 hours back, I'm sorry, because it's a hourly data set. So basically it follows a pattern of every 7 hours. That's what it thinks like. Now what I can do is wherever it's significant, those lags, I can create as features and build a new model, or I can just take it as it is and then run it, right? I can deploy it. So how we can deploy it? I'm going to run it as it is, but if you want to build a new model also, you can go and build it, right? So I prefer to run it as it is mostly if the output is good, if the metrics are good. The reason is, even though these features are telling it's non-significant, it might still contribute a small extent to the output of the model, right? So that's the reason I like to do it that way, but the other way is also perfectly valid, right? Now what I'm doing is basically I am taking the all the coefficients over here, and then I'm just taking the values out of it, right? I'm taking from the first till the end, because that are the coefficients. The first value is the constant. If you remember the linear regression equation, it is nothing but y equal to mx plus c. C is a constant, but the m and x can be an multiple input, and m can be a coefficient matrix that you can have, right? So I'm just taking first to end value. I'm creating coefficient array. If you see the coefficient, I will have around a size of 21. The reason I have 21 is I have three features. There are 7 lags, 7 into 3, 21. So I have 21 coefficients, right? Now I can print the coefficient array also. Now what I'm going to do is I'm going to take this coefficient, multiply it with my input value, and then add the constant. So that becomes our linear equation, right? So what I am doing in this case is I'm going to the training data frame and taking the last 7 values. I just want to validate whatever the model predicted plus whatever we are doing manually is fine, because we can do a mistake when we are doing a matrix multiplication or something like that. I just want to validate it. So I'm taking the same thing that we did for result.forecast. I'm taking the past 7 values so that I can predict the next value. So I have the df train with lag 7 values, right? Now I have the lag. What I'm doing is I'm just stacking this value into a single row. I am transposing it and getting an dot values will give me an array. That's what it is. So once I run these two commands, you can see the output, 3 commands. You can basically see the output. I have 1 bar 21. I have 1 row and 21, you can assume columns or 21 instances of it. And this is how my output looks like. Basically 63, 9, 4, 58. And if you see on the top, this is nothing but our matrix from bottom to top. The reason we are reversing from bottom to top, because if you see I'm selecting from bottom to top, the reason is if you see the coefficient matrix, it starts from L1, L2, L3, L4, L5, L7 of each variable. So basically my lag 1 is in the bottom till lag 7 in the top. So that's the reason I'm reversing the order, and that's the way it is. Now I have my coefficient matrix, I have my input matrix. I can just do an mx, that is y equal to mx plus c mx, plus I can add the constant, and that's what I'm doing. I am doing an np dot dot of input array and the coefficient array, plus I am going to my coefficient matrix and picking the first record, which is nothing but the constant, and I am adding it. So once I run this, I am going to get a value which is my next forecast for appliance, 44.3459. And if you go on the top, if you go to the result.forecast, on the top that we did, yeah, it's 44.34. So either you can take the model, save the model and deploy it, or you can just take the coefficients and everything and build your own implementation. The reason I might want to do my own implementation is now I have, first thing, I have a good vectorized implementation. And if I have a lot of data and I need to do a lot of forecast, I can use GPUs to just run this equation. It's easy for me. By default, the VAR model does not support GPU inferencing. So now I can run it on a GPU. I can have a very heavy vectorized, and I can get I can concurrently fire a huge matrix and get a series of future forecasts. That's the reason I might want to do it. So that's about it about the VAR model. And what I will do is I will go back to the ARIMA model in my future videos and complete that. Thank you very much.